Hi guys, today we're going to be covering a couple different integration techniques that will help us solve new types of integrals that we haven't dealt with before. Some of it might be a review, but these techniques are important for Calc 2 and they'll carry over obviously into Calc 3, so we should really be wanting to review these. The first thing we'll start out with today is integration by parts. And while that is similar to U sub in the sense that we're now taking new variables and assigning them to different parts in our integrand, it's different due to the fact that we're using it to undo product rule rather than chain rule. Okay, so IBP undoes product rule. U sub, what we've already been practicing and what we've known before, undoes chain rule. And so we may need U sub later on in our problems, but starting out, it won't be enough for these new integrals that we're going to be looking at. Okay, so our first example here, we want to find the indefinite integral of x to the fifth times e to the x squared power, and we want to integrate that with respect to x. So looking at this, U sub in and of itself will not work, because when we find an antiderivative, the chain rule coming back will give us a different integrand. Okay, so we're going to be doing something else where we pick one of these pieces of our integrand to call u, and whatever's left over we'll call dv. And then from there we'll recall our formula. One other side note for us is an acronym that will help us in most cases to choose which part of our integrand to choose for u. So depending on which type of function shows up first in your integrand is what you're going to try to choose for u. And this will work most of the time. Enough of the time for us to remember it and for it to be worthwhile. So logarithmic, ln functions, or log to any other power. The I stands for inverse trigonometric functions, so tan inverse, sine inverse, cos inverse, etc. The A here stands for algebraic, T for trigonometric, so just your normal sine, cos, tan functions, etc. And then lastly, exponential. So we're going to look at our integrand and we're going to see which type of function occurs first, and then we're going to choose that for u. Okay, and so here e is an exponential function, that's the very last in our acronym. Here we have an algebraic function, x to the fifth power. So that's what I'm going to choose for u. But here's the problem. If I just say u equals x to the fifth, then what that does is that leaves e to the x squared as my dv. And in order to find v, I'm going to need to integrate this function. But looking at that, that is not going to be easy to do. It's not going to be possible with u sub. Okay, so there is actually a clever way to get around that right there. And all we're going to have to do is choose u as x to the fourth. Because in that case, what that leaves behind for our dv is x times e to the x squared power. And that can be integrated quite easily with the u sub. So when we go to find v, we know that it's the integral of dv, which is the integral of x times e to the x squared dx. Okay, and to integrate this, I'm going to do a little bit of u sub in my head. I know that I took the derivative of e to the x squared power, and a 2x came to the front with the chain rule. But in my integrand, I don't have the 2, so I'm going to divide by that, and I'm going to say times a half. Okay, and so then I see that that would work if I try to take this derivative backwards to get to here. Okay, and then all that's left here then for our setup is finding du. Now that allows us to find this because we could do a recall over here. The integral of u dv uv minus the integral of v du. Okay, and then we can go ahead and plug in and see what we get. So for our original integral, we got uv minus the integral of v du, 1/2 e to the x squared times du. And then what we actually see going on is that in this new integral that showed up from the first iteration of IBP is that we'll actually need to do it again. Okay, we're going to need to do IBP again on that one. Okay, so we will do another u and v. Okay, so here, let's do this similar thing where we save one of those copies of x to be put in our dv. And actually what we could do before we do that is actually simplify this. We could go ahead and turn that into a 2 because we have a 1/2 times 4. So I'm going to rewrite that actually real quick. And then now over here, we're going to do that similar approach that we just did in step 1. So we're basically saving 1 power of x to be put in our dv. Because then it allows us to integrate it pretty quickly with a u sub. And then find our du. Okay, so now we have to go back and we are going to do IBP on this second resulting integral, but the piece out front will remain the same. Minus uv. U times v, I see the 2 and the 1/2 cancel out. Minus the integral of this v and du. Okay, I'll combine the 4 times 1/2 is 2. Okay, and then now I see I'm going to deal with my signs, my positive and negative signs. I'm going to make sure I distribute those out. But it looks like that last integral I have in my expression will be simple enough for us to evaluate, and then we'll be done integrating for this. We will have found our antiderivative. So it's going to be plus the integral of 2x e to the x squared. And then now I see that if I did a u sub on this integral right here and I said u is equal to x squared, then my du is already in my integrand. I have 2x dx right there. So really I'm just integrating e to the u. In other words, this is just really a derivative rule in reverse here, working on that chain rule backwards, doing u sub. So I don't really need IBP or anything like that. I can do that one in my head. And then now I'll put on my plus c, and I've found my antiderivative. But an important thing to note here, obviously, is our Lie acronym. It won't work all the time, but it will work most of the time. And then another important factor here was the fact that we chose u to be x to the fourth rather than x to the fifth. And it's important that we make those conscious choices so that we can leave behind whatever we need in our dv to allow us to integrate. And then doing IBP just twice got us to our final answer right here. Okay. I'm going to do one more IBP example for you guys with a slightly different looking function so that we can see a different case in which this would apply. Okay. I'm going to get all this erased. Alright guys, for our next IBP problem, we're going to take a look at a slightly different looking integrand. One that we wouldn't necessarily expect to use IBP on, but it will work quite nicely for us. So when we look at integrating arctangent, the tan inverse function, we don't know any derivative rules in reverse. We don't know anything, we don't know a function that we can take a derivative of directly and then just get back tan inverse. So we're going to need a slightly different approach here. Obviously a u sub is not really going to work too well to our favor because again we don't know how to integrate just the tan inverse function. So we're going to try IBP. What we're going to do there is assign u to be really the only thing we see in the integrand. But then remember that what we're leaving behind for dv in this case is actually just the dx, the differential. So this will be fairly common in these type of problems where you're just going to have dx left to be your dv. And that's perfectly fine because it's a lot easier to integrate. I mean, v equals x in that case. And then we can take the derivative of tan inverse. That should not be a problem for us. It's really just the integration, which was our problem in the first place here. So we'll recall the derivative of tan inverse is 1 over 1 plus x squared dx. And now we have all the pieces that we need to go ahead and proceed with our integral. So we get uv x times tan inverse of x minus the integral of v du. And then now we are left with an integral that is a lot easier for us to evaluate. Here we're going to do a u sub. We're going to call that whole denominator u. Du in that case is 2x dx. And then we're just going to modify that equation there by a constant. We're going to multiply both sides by a half. And now, because I see that x dx here in my integrand, I can go ahead and replace that with a 1/2 du. Okay. And now when we're left with the integral of 1 over u, or in other words, u to the negative 1 power, we can't use power rule. In this case, we actually need to remember that the integral of 1 over u is ln of the absolute value of u. Power rule would not quite work there. So we're just going to get minus 1/2 ln of the absolute value of u. And because we're going to be substituting back in, we want to give our answer in terms of x. We'll just go ahead and put that directly back in there. And then we won't forget our constant of integration plus c. And so then just after doing IBP once, we've found our antiderivative. We're going to look at one more partial fraction decomposition problem. Okay, so for this problem, guys, our first first step is really realizing our weaknesses here of knowing that we can't quite do a U sub. We can't pick out anything that's already in there to be a du, and we can't really mess with it to make that du appear. We also can't factor it in a way that's going to be helpful to us. So that's going to be a little bit of an issue. If we did complete the square on the top, we might be able to make it look different, but that will probably just get us to the same point that polynomial long division will. And that's going to be a skill that we want to learn anyways. The reason we're doing polynomial long division is because the degree of the bottom is not bigger than the top, they're equal. So there's at least something that can be divided, some quantity of x squared plus 1 can go into the top, and then there will be a remainder. Okay? So on the side here, we're going to do a long division. We'll put our numerator inside here to be our divisor. Okay, and then we're dividing by x squared plus 1. And we ask ourselves, what number do we need to multiply x squared by to get this term, to get our first term? The answer there is 1. We then distribute the 1 to our x squared plus 1, the thing we're dividing by, and we get down here. And then we subtract that. That takes away, that cancels out, so that goes away. All we're left with is a 2x. 3 minus 1 plus 2. So this piece, 2x plus 2, is our remainder that still needs to be divided by x squared plus 1. Okay. At this point, we could do partial fractions, definitely, because we have a irreducible quadratic. We would go ahead and set equal. We would use a technique here in our book. We only have one irreducible quadratic factor, okay, so we have to go ahead and set it equal. But in this case, in this problem, it's actually a little bit easier than that. We're just going to do an algebra move, and we're going to split this up. We're going to split it up into two pieces. And then look at each one separately. So to integrate one, pretty easy, we just get x. Our next piece here requires a u sub. Alright, we're going to let u equal x squared plus 1. And then we have 1 over u. Our du shows up directly in the top. If this is our u, then our du is 2x dx. So we have our du. And then we have it to the negative 1 power. We can't use power rule, but we're going to use ln. And then here, if we pulled that 2 out as a constant, we would see a derivative rule in reverse. We would see the inverse tangent, 1 over x squared plus 1. So that is actually just a derivative rule in reverse. Okay, so in this case, we did not need to really do much of a partial fraction decomposition after we did that long division, because we were able to just do a quick little algebra move that allowed us to get two much easier integrands to show up in our problem.